We are taking a look at inverse functions in this lesson. An inverse function undoes a function, meaning when you write the composition function, so take a look down here for a reminder of what the composition looks like, you'll get x alone. Note that the inverse is not always a function, so we're going to look at how to tell whether or not it's a function. All right, so my example, if f of x equals 2x, that is the inverse of g of x, which equals 1/2 x, because if you perform that composition, so if we take the g function, 1/2 x, substitute it into the f function for x, and simplify, 2 times half x is x. And it will work the same if you flip the order of the composition. All right, so we have two tests to graphically determine if a graph is a function or if its inverse is a function. So the vertical line test, remember, if you're looking at a graph, any vertical line, if a single vertical line touches the graph more than once, it is not a function. So for the inverse, we look at the horizontal line test. If any horizontal line touches a graph more than once, its inverse is not a function. So we're going to start with looking at that. So first we are going to determine whether or not the graph is a function, and then we'll look at whether or not its inverse is a function. So I'm going to start by looking at vertical lines. So if I am looking at any vertical line that I place on this graph will only touch the graph once. I can't see a single spot where I can put a vertical line that would touch the graph more than once. So yes, this is a function. All right, to check for its inverse being a function, we use the horizontal line test. So if I'm looking along here, touches the graph once, but if I move it up a little bit, here and here, it touches the graph more than once. A single horizontal line touches the graph more than once. So it does have an inverse, but the inverse is not a function. So next, let's take a look at how to write or find the inverse of a function. So the process for finding an inverse, what an inverse does is graphically reflects it across the line y equals x. So algebraically, when we find the inverse, what we do is we first replace f of x with y, and then we flip the x and the y, the same way they would get flipped on your graph. So this becomes x equals y squared minus 9, and then we solve for y. So first I'm going to add 9 to both sides and take the square root. Now in this case, in order to get the full inverse, when we square root, we have to use the positive and negative square root of x plus 9. And then just a little bit of function notation, we can rewrite this with f. It looks like to the negative 1 power, but it's read f inverse of x equals plus or minus the square root of x plus 9. One more example of writing the inverse. Again, start by replacing f of x with y, and then flip your x and y's. Now we have two x's on this one, so everywhere we see an x, it will turn into a y. All right, so to solve this, I'm going to multiply both sides by y to get the y out of the denominator. And then in this case, because when I subtract y, which I'm going to do to get both my y's on the same side, they're not like terms. So I'm going to start with yx minus y equals 5. And then to finish solving for y, I'm going to have to factor that out of those two terms. So I'm going to factor the y out. And then I can finish solving for y by dividing both sides by x minus 1. So the inverse is y equals 5 over x minus 1. Rewriting this with the function notation, we get f inverse of x equals 5 over x minus 1. And I just realized I also asked for domain and range. So I'll go back to the example 2 to get domain and range as well. So if we're looking at our original f of x function, the restricted domain, x cannot equal 0, range would be all real numbers in this case. That's pretty close. We'd have to check the asymptotes, but I'm going to fudge a little bit. And then on this one, the restricted domain would be where the denominator cannot equal 0. So x cannot equal 1, all real numbers. Jumping back here, domain and range for any quadratic would be all real numbers. Looking at the inverse, remember for a radical, the domain would be what makes the value under the radical greater than or equal to 0. So x would have to be greater than or equal to -9. And because of that plus or minus, the range in this case is all real numbers. Typically when you graph, remember when you graph a radical, we would get something like this, but that plus or minus finishes off that sideways parabola for us. So we do get all real numbers on that range. All right, last example, we are going to test whether or not these functions are inverses of each other. So the way we do that is we use the composition. Now, if the first composition gives you x, you have to check the second one as well, g of f of x, in order to make sure that they both work. But if this one doesn't work to give you x, then we know it's not an inverse. So we're going to substitute our g function in for x in our f of x function. And I should probably use a -4 here. And then we have to simplify, so we have to remember how to add fractions in the denominator there. We're going to multiply this by x minus 4 over x minus 4 to get the common denominator. So this becomes 4x minus 16 over x minus 4. Combining our like terms in the numerator of our denominator. So we've got 5 plus 4x minus 16. We get 4x minus 11 all over x minus 4. And then we have division. So I'm going to look at this fraction bar as our division, and I'm going to multiply by the reciprocal. So I'm going to flip that denominator. And I would multiply in the numerator 5x minus 20 over 4x minus 11. Now I could maybe factor and simplify, not seeing that off the top of my head. Nope, the denominator doesn't factor. So this is as quote simplified as it gets. If you start to substitute in and it starts to get really complicated like this one, it's probably not an inverse. This did not simplify to just x. So no, f and g are not inverses of each other. And here are your two U-try questions.